Hello, my name is Elizabeth, and today we're going to be working on this problem from Homework 5. So, let's get started. Okay, let A be a subset of the Cartesian product of the set of natural numbers with the set of natural numbers, and define the relation tilde on A such that for any pair AB and pair CD in our set A, if the pair AB is related on tilde to the pair CD, then this implies that the absolute value of A squared minus B squared is equal to the absolute value of C squared minus D squared. So we can see in the example they give us that the pair 3, 0 would be related to the pair 4, 5 because they would both evaluate to 9 by the definition of the relation. Okay, so now let's argue that tilde is an equivalence relation on A. So what it means to be an equivalence relation, for tilde to be an equivalence relation, we have to show that tilde is reflexive, symmetric, and transitive. And this is just by the definition of an equivalence relation. So first, let's show that tilde is reflexive. In order to do this, we need to show that for any arbitrary element in our set A, we should have to show that that element is related to itself. This is by definition of reflexivity. So let's apply our definition of the relation now, and we will see that we want to show that the absolute value of A squared minus B squared is equal to the absolute value of A squared minus B squared. And now, clearly this holds true, so therefore, we've shown that for any arbitrary element in our set that it is related to itself, therefore we can conclude that tilde is reflexive. Okay, so now to show that tilde is symmetric, we have to show that for any two arbitrary elements in our set, let's say we have a pair AB and a pair CD, we want to show that if the pair AB is related to the pair CD, then this should imply that the pair CD is related to the pair AB. So now, let's assume that this part of our statement holds true. Then, applying our definition, we can conclude that the absolute value of A squared minus B squared must be equal to the absolute value of C squared minus D squared. Now let's see from this that if we apply by the symmetry of equality, it must hold true that the absolute value of C squared minus D squared is equivalent to the absolute value of A squared minus B squared. And now, see that this right here, is exactly what we were trying to prove right here. So therefore, we can conclude that tilde is symmetric. Okay, and now finally, we want to show that tilde is transitive. In order to do this, we need to show that for any three arbitrary elements in our set, let's say we have an element AB, an element CD, and an element EF, all in our set A, we want to show that if the element AB is related to the element CD and the element CD is related to the element EF, then this should imply that the element AB is related to the pair EF. Okay, so now let's assume that these two parts of our statement hold true. And now applying our definition of the relation, we can see that the absolute value of A squared minus B squared must be equivalent to the absolute value of C squared minus D squared, and the absolute value of C squared minus D squared must be equivalent to the absolute value of E squared minus F squared, just by our definition. Now if we apply the transitivity of equality, we can see that it must hold true that the absolute value of A squared minus B squared is equivalent to the absolute value of E squared minus F squared. And now, once again, see that this is exactly what we were trying to show in order to prove transitivity. Therefore, we can conclude that tilde is transitive. And now, since we've shown that tilde is reflexive, symmetric, and transitive, we can thus conclude that tilde is an equivalence relation on A.